Integration by partial fractions, part 2. We're going to be looking at a second set of integration of rational functions that look more similar to this. Now, what's the difference between this problem versus all the other ones that we've been doing? Well, if you take a look, in the denominator, the factored form has one factor with an exponent of 2. It's squared. Therefore, when we split it up, and you want to split it up into something like this, two fractions that look like this, the common denominator in this case will not become x minus 1 squared times x plus 1. The common denominator in this form will become x minus 1 times x plus 1, which is not what we want. We need that to be this to the second power. Now, if I take this x minus 1 and take it to the second power, and I want to add it to a second fraction with a denominator of x plus 1, then now the common denominator will become this, correct? I would only have to multiply the top and bottom of this fraction by x plus 1, the top and bottom of this fraction by x minus 1 squared. However, this is actually an incorrect way. Let's take a look at what happens if we continue doing this. Well, the common denominator, I'm going to have to multiply top and bottom by x plus 1. So I'm going to do ax plus a, distribute that directly in. I'm going to have to multiply this fraction, top and bottom, by x minus 1 squared. So the b I'm going to have to multiply by x minus 1 squared, which I'm actually going to square out for you first here. Right? And all of that will have to equal to this numerator of 4x. Right? So taking it further, I got ax plus bx squared minus 2bx plus b should equal to 4x. I can see that, well, it looks like I have an x squared term here, but I don't have an x squared term here, so b looks like it's already 0. If I take a look at my constant, there are no constant, so it looks like a here plus b, a plus b has to be 0. Therefore, if b is 0, a has to be 0 also. Now, if that's the case, then that 4, it looks like the coefficients of x has to be ax minus 2bx, a minus 2b has to equal to my 4, and 0 minus 0 is equal to 4. So again, something is missing, something is awry with this method. So this is actually not the proper decomposition of this fraction. Why is that? Well, this is not the only way to create this common denominator. We have what we call a double root here, so we need to take into consideration the fact that there's a factor of x minus 1. So let's try that again. The proper decomposition is going to be you have an a, you definitely have your x minus 1 squared. But embedded in that, you have an x minus 1 also. Let's take a look at what happens here. So now, what is the common denominator of all three of these? Well, this one has x minus 1 times x minus 1, so all that one's lacking is your x plus 1. So I'm going to multiply top and bottom by x plus 1 here. This one has one factor of x minus 1, but it needs one more, right, for that common denominator. Plus, it needs an x plus 1 as well. So I'm going to multiply the top and bottom by x minus 1, x plus 1 here. This one only has a factor of x plus 1. It's missing factors of x minus 1 squared. So x minus 1, the whole thing squared. Okay? This will become the proper decomposition, and we want that to equal to 4x over x minus 1 squared times x plus 1. Now, if that's the case, if you take a look, I can distribute that in, ax plus a plus b times, this looks like it's a product of a minus b times a plus b, so I get x squared minus 1 plus c times x squared minus 2x plus 1. And that should equal to 4x. Now, all of this, I won't actually make you sit there and watch it for me, but watch it with me. But if I multiply all of this out and set all my systems equal to each other like this, then you'll see that A is equal to 2, B will equal to 1, and C will equal to negative 1. Okay, so now if we go back up here, and we want to rewrite this fraction this way. So this will all become the same thing as A, so your 2 over x minus 1 squared, plus your B, which is 1 over x minus 1, plus your C, which is negative 1 over x plus 1. Now, in this case, to integrate, you will get 2, and this is going to be 1 over x minus 1 to the negative second power. So I'm going to get x minus 1 to the negative first power over negative 1, right? Plus the integral of this one, which is the natural log of x minus 1, minus, because I'm going to bring that down here, the natural log of x plus 1, plus c. Just to simplify one more step, I get negative 2 over x minus 1 plus natural log of, this is kind of a good time to go over it, natural log, if I have the difference of two natural logs, I can combine that into x minus 1 all over x plus 1 plus c. Moving on to the next kind of problem, let's take a look at what happens for something like this. It looks like what's happening here is pretty much the same idea. Let's factor and see what we get. If we factor out the denominator, we get, factor out the x, and you get x squared plus 4 dx. Now in this case, if you take a look, I cannot factor this anymore, and my highest degree here within this factor is 2. So the decomp could look a over x, that's one of the factors, plus b over x squared plus 4. And set that equal to 2x squared minus x plus 4 all over x squared plus 4. Now in this case, if you take a look at the denominator, the common denominator will still become this. That part is correct. However, the numerator, if we don't take into account the fact that the highest degree in the denominator here is a 2, then we're actually going to lose one of our terms. So what I'm going to do here, if your highest degree is 1, like every other problem that we've been doing, then we drop it 1 degree to x equals x to the 0 and you leave it a constant. But if it's to the second degree, I actually want to take it only 1 degree less and put in a bx plus a c. So that will start to take care of every term in this numerator. And you can test it without the c, without the bx plus c and just a b to see if you can actually find this. But you'll find that you cannot. So this would be the proper decomposition for this fraction. Okay, so now if you do it the exact same way, you finish it the exact same way, the common denominator will be x times x squared plus 4. So the a, I'm going to need to multiply it by x squared plus 4. The bx plus c, the entire thing, I'm going to have to multiply top and bottom here by x and set that equal to 2x squared minus x plus 4, and so forth and so forth. Now if you continue with this, you'll see that a is equal to 1, that b is equal to, also equal to 1, and c will equal to negative 1. So after you've done all that work, and I'm going to come back here because there's actually one more thing that we have to go over. If you take a look, this decomposition will become, 1 over x plus 1x minus 1 all over x squared plus 4 dx. Now integrating this first part is easy. The integral of 1 over x is the natural log of x. Now how do I integrate this though? This part right here. So let's do that. How do I integrate x minus 1 over x squared plus 4? Well, you can try a u sub, because I can see that the derivative of the bottom could exist in some form at the top. If I do u is equal to x squared plus 4, du is equal to 2x dx. But remember, this is multiplicative. And if x dx is here, x times dx, well, do I distribute? This is always multiplicative. No, so u sub here will not work. Okay? So what you can try to do here, however, I can try splitting it up into x over x squared plus 4 minus 1 over x squared plus 4. I just split up this function, this fraction, into 2. Now from here, for this one, u sub is definitely possible, right? Where u is equal to x squared plus 4. So I'll set u equal to x squared plus 4. du is equal to 2x dx. So I would have 1/2 the integral of 1 over u du. And then I'll have this to take care of here, which, again, we'll take a look at in just a little bit. To finish this up, you'll get natural log of absolute value of x plus 1/2 natural log of x squared plus 4, right? And then now I just have to take care of this. Now in this case, if you remember, wouldn't it be really nice if I had the integral of 1 over x squared plus 1 dx as opposed to that 4? Why? What is the integral of 1 over x squared plus 1? That turns out to be arctangent x plus c, right? Well, there's a variation of this that allows me to integrate 1 over x squared plus an a squared dx. And that integration really is a form of completing the square. It's going to be 1 over a arctangent of x over that a plus c. Okay, so in this case, if you notice, 4 is going to be 2 squared, right? So a is going to be 2. So that will give me the integral of 1 over x squared plus 2 squared is going to equal to 1 over 2 arctangent of x over 2 plus c. Okay. So now let's take a look at some integration, some of the decomposition, and see if you can come up with them. How would you start integrating this? What would the decomposition be? How would you start integrating this one? Don't forget, there is a highest degree of 2 right there. You can't factor the bottom. How would you integrate this one? This decomposition, how would you integrate this? How would you decompose this? Here's the next one. Here's one more. It's already factored for you in the denominator. Do you remember how to factor this? And the last one, this one.